Chapter 4, Lecture 4. Okay, so in the previous chapter, we have talked about the arithmetic operations, some branches and call instructions that we can use for conditional statements and for calling a function. Now, these were related with the assembly side of it. Now, I want to talk a little bit on the hardware side now, which we are going to see the resources inside of the AVR so that we can interact with the outside world. Because AVR has got many pins and there are lots of ports in that microcontroller, which we can use them either as an input-output ports or some other specific functions. So in this chapter, which is chapter 5 in the book, we are going to talk about the AVR pinouts, the structure of I/O pins, I/O programming, and I/O bit manipulation. So it's all about input outputs, and AVR families has got many input output ports depending on their pinouts. So for example, 8-pin AVR has got port B, 64-pin AVRs has ports A to F, and 100-pin AVR packages or types or families has got ports A to L, and 40-pin AVRs has got ports A to D. Now, ports, when we talk about ports can be either inputs or the outputs. And in addition of being used as a simple I/O, as I already mentioned, each port has some other functions like analog to digital conversions, timers, interrupts, and serial communications, which we are going to see those in the following lectures. Now, each port that we are going to see has got 3 I/O registers associated with it, which they're in the SFR, which is special function registers in the I/Os. Now, what are those registers? The first one is DDRX. Now, DDRX register is an 8-bit register, 7 down to 0. It's known as data direction register. So what is important over here, if you set DDR as 1, that means you are setting the port to be out. If you are setting it to 0, you set port to be an input port. Now, DDRX decides the direction. If you set it to 1, it makes all port individual pins, all of them as outputs. If you set to 0, all of them are going to be inputs. Another register that we have got in I/O is port X. I'm saying X because that can be A, B, C, D, E, depending on the AVR package that you are using. So port X is also 8-bit register. And port X is actually the output port. So if you want to send out a data, you put your value into port X, and that will be sent out through the pins. And conversely, pin X, again 7 down to 0, known as port input pins. So if you want to read data coming from outside, we read pin A or pin B. Okay, so this is how we can interact with outside world. Now, once again, DDRX I/O register is used solely for the purpose of making a given port an input or output port. And to make an output port, we write ones to the DDRX register. And to make it input, we write zeros to the DDRX register. Now, you can see the structure of the pin over here that we can demonstrate each of the individual registers with a table. Now, when DDRX, which is a direction, is 0, now what will happen? This will be 0 converted to 1, and port X, we can put any value over there. When they're ended together, this is actually, if it is 0, it's going to be an high impedance, okay? Because this is going to be activated and the resistors will pull this pin higher. Now, if the DDRX is 1, that means this is going to be 0. Okay, so this is going to be activated. Okay, and what will happen over there? Whatever you have got on port, which is 0, it will be sent out. Okay, so when it is 0, and this one is 0, this is not going to be activated, so it's high impedance. And when this is 1 and this is 0, that means you're activating the tri-state buffer over here, and this is going to be sent out. Now, when port X is 1, while DDRX is 0, this is going to be activated because both of them are going to be 1, and it's pulling up. Now, when DDRX is 1, and this is 1, you're actually sending out, because tri-state will be activated, you are sending out 1. Okay, so this is how we can use the output over there. So if DDRX bits not set to 1, the data will not go from port register to the pins of the AVR. And you can see the architecture of the digital I/O circuit. We have got the data bus, the pins over here. We have got the gate and the pull-up part. We have got the tri-state over here. So we can activate it, the tri-state, and whatever we have got, it will be transferred to the output pin. Now, in order to have write a value to the output port and you want to read, you just need some delays in between those. Okay, so you can use no operation instruction between writing and reading the same ports. You have to be careful. Right, here is the first example that we want to write a program that make all the pins of port A to be 1. Now, how do we make all the pins of port A be 1? Now, that means DDRA is going to be set to 1, all ones, 1, 2, 3, 4, 1, 2, 3, 4, which is equivalent to 0 hex FF. Okay, and port A is also going to be 1, 1, 1, 1, 1, 1, 1, 1. Now, this means that this is also going to be 0 hex FF. So how do you write the code for it? Let's initialize 0 hex FF. And as this is an IO register, I can directly use out instruction, which I want to put this value into port A, which is R20. And I also want to put this value into DDRA R20. So either DDRA first or port A first, it doesn't matter. You can write it either way. Now, these three instructions are actually going to set all the pins of port A to be 1. Another example, toggle all 8 bits of port B forever between 010101 and 101010. So 010101 is actually what? It's 55. So 01010101, this is 5, this is another 5. So 0 hex 55 can be used. And we have to toggle it to 10101010, which is A and A. So 0 hex AA. Now we know these values. We had to toggle all 8 bits of port B. Port B is going to be used. And use delay between on and off states by calling delay subroutine. We don't need to define it, we just need to call it. So that means our port B is going to be an output port. So let's say R16 is going to be 0 hex FF. So I'm setting those to be 1. And then this is going to be out DDRB R16. So I can say that port B is an output port. Then what do I need to do? LDI R16 0 hex 55, which is 010101, and I have to send that out to port B, so it will maybe turn on the LEDs or something like that as 0101. Now once I've done that, I have to call delay so that I can see that difference by I, and I can initialize R16 0 hex AA and send it to port B R16. Then I call delay again because I want to see that difference. And then I have to repeat this forever. So I can say R jump L1, that L1 has to be over here so I can restart. Okay, so this is going to be repeated forever. Example 3, an active high 7 segment is connected to port C, display 1 on the 7 segment. So 7 segments is given, we have to display 1. So which segments are activated? Segment 1 and segment 2 are activated. Now it's connected to port C, so that means DDR-C is going to be an output port. And port C, as we are activating pin 1 and 2, that means 1, 2, 3, 4, 5, 6, 7, 8. Now, 7654321 So 1 and 2 is going to be activated in order to turn on 1, and rest will be zeros. So what is this in hex? First 4 are zeros, so 0, and this will be 6. So we can say that port C is going to be 0 hex 06. Now we know what we are going to program. So LDI R20 0 hex 06, and that will be out port C R20, and I also need LDI R20 0 hex FF for DDR. So out DDRC, it's going to be R20. And then our jump L1, we just wait over here. So this is how we can use port in order to activate a 7-segment or in order to send out a data. Another one, read the data present at pins of port C. So that means we are going to read it. That means port C is going to be configured as an input port and send this data to port B indefinitely after adding the value 5 to it. Okay, so port C is going to be an input port and port B is going to be an output port. So DDR-C is going to be 0 hex 00 input port, and DDR-B, it's going to be 0 hex FF. So let's write the code. LDI R16, it's going to be 0 hex 00, out DDR-C R16, LDI R16 0 hex FF, out DDR-B R16. So we set the port directions. Now we have to add value 5, so I will initialize that as well. LDI R17 5. Now I have to read pin C. So in order to read it, I use in instruction. Where do I need to read? I can specify a register. So pin C value that we are reading is going to be copied into R16. Then I have to add that value with 5. So 5 will be added to R16, and that will be sent to port B. Which value? R16, which is the result. And then I have to repeat that again for the next input. Okay, so setting the ports, setting the value that I want to add, read pin C into R16, add 5 to the R16, the pin C value, send it to port B, and repeat that again. So sometimes we might want to access only one or two bits of the port instead of the complete port. Or you might want to set specifically a couple of pins to be an input and a couple of pins to be an output. So there's a strong feature of AVR I/O ports that you can easily access to their individual bits of the port, and you don't need to alter the rest of the bits in that port. So we have got instruction SPI. So SPI is actually set bits in IO reg. Okay, and the format is SPI the IO reg and the bit that you want to set. So for example, I can say SPI port D bit 0. So this is actually port D0 will be 1. Or maybe SPI DDRC is going to be 5. So let's say this is DDRC. 1, 2, 3, 4, 5, 6, 7, and 8. 7, 6, 5, 4, 3, 2, 1, 0. Bit 5 is to be set, and the rest will be zeros. Okay, so I can use SPI over there. We can also use CBI, similar to SPI, and this is known as clear bits in IO reg. So the format is CBI IO reg, and we have got the bits. So for example, CBI port D 0. So only the port D 0 pin or 0 bit is going to be 0. Or I can have CBI DDRC bit 3. So again, 7, 6, 5, 4, 3, 2, 1, and 0. Bit 3 is going to be 0. So these are all demonstrated. Again, you can see from the datasheet extraction, they are the 2-cycle instructions because you have to read, modify, write requirement in the execution. And each of them, if you are using ports, they are all 8-bit ports. So it can be applied to any of these 8-bit ports. So a few more examples. It says, write a program that toggles port A 4, so port A pin 4 continuously. So what do I need to do over here? I can just say SPI First, I have to set it DDR-A to bit 4 to be 1. And then I have to set port A bit 4 to be 1. And then I have to clear that. So toggling means setting and clearing. CBI port A bit 4. And repeat that forever. Okay, so setting, clearing, but we have to first define it if it's going to be an input or an output. Another example, an LED is connected to each pin of port D. Write a program to turn on each LED from pin D0 to pin D7. Call a delay module before turning on the next LED. Okay, so we are going to write it, light LEDs one bit at a time. Now, starting from LDI R20, we have got 0 hex FF. So we are setting the port D to be an output port. And first, I set the port D bit 0. Then I call delay is a routine so that I can wait a little bit. Then turn on the next pin. Then call delay again. Again, set another one. 2. Call delay. SPI port D3. And it goes up to SPI port D7. And I have to call delay. Okay, so this is turning 1 bit at a time from 0 to 7. So we also have two other instructions for the I/O ports, which they are like a conditional instruction. So SPIC and SPIS is skip if bit in I/O register is cleared. So there's a condition. We can skip the next line. Again, it can be applied to 32 of the I/O registers. So for example, you can say SPIC port D0. So if the port D0 is cleared, then it will skip increment and it will just say LDI R19 hex 23. SPIS conversely to clearing it, it will check for if it is set. So if port D0 is set, then skip instruct incrementing and initialize the number. So write a program to perform the following. Keep monitoring PB2 bit until it becomes high. And when PB2 becomes high, write value 45 to port C and also send high to low pulse to PD3. So first of all, in order to monitor PB2, that means it has to be an input port. So I can just say only for bit 2, CBI DDRB bit 2. So I set that to be an input port. Then LDI R16 0 hex FF. So port C is going to be out, DDRC R16, port C is an output. And then I also need to say that port D bit 3 is going to be an output. Well, I can set that SPI DDRD bit 3 to be an output. Now we have got the direction of the ports. Then in order to monitor PB2, I can just check, because we have to monitor if it is high. I can use this SBIS. If the bit is set in pin B2, then I can skip the next instruction. So R jump L1. Otherwise, if it's not set, I have to keep monitoring it. Wait until it is set. And if it is set, we skip the next instruction where we are looping, and we go for LDI R16. It's going to be 0 hex 45, because we have to write that to port C. And I'll say out port C R16. And high to low pulse SPI port D bit 3 to be 1, and CBI port D to be cleared. And once it is done, I'll jump here, and that will be also here. Okay, so we wait there. So first, we monitor the pin B2, check if it is set. If it is not set, repeat. If it is set, skip that one and put the value for hex45 into port C and send the high to low pulse to port D pin 3. And the last example that we are going to see, switch is connected to pin B0 and LED to pin B7. Write a program to get the status of the switch and send it to LED. So that means pin B is going to be an input port. So I can directly say CBI DDRB 0 and SBI DDRB 7 to be 1. So this is in, this is configured as out on the same port. So I have to check if the switch is turned on or closed. So SPIC, if cleared, pin B0, that's I want to check. I can say R jump over, and I have to jump somewhere else. Otherwise, if it's not cleared, then CBI port B7. So that means LED will be turned off. Okay, and our jump again. So we have to do that again. So over will be here. So we can say that SPI port B7, which will be turned on. Now this means that when we are checking if it is cleared, we go to CBI and we turn off the LED. So that means the switch is off. And if it is on, we jump to over and we turn on the LED. And after that, we perform our jump again. So we return back. Okay, so in this short chapter, we have covered the I/O ports, how we can interact with the outside world by setting the I/O ports input as an output. And DDRX is a direction register that we need to set, and we can use port register, port X, port A, port B, port C, or something in order to send out the data. And in order to read the data from the outside, we have to use the pin register, which they are all placed in the I/O register or special function registers. Thank you.